So without further ado, I really want to welcome Professor Martelotto on the stage. He's going to present the first keynote speaker of today morning.
Good morning, colleagues, dear colleagues, and ladies and gentlemen. Sorry for this little technical problem, for this delay. We will try to recover along the day. So it is my great pleasure and honor to introduce our first keynote speaker of the day. Dr. Xudong Yang graduated at the University of Tsinghua. I hope I pronounce it correctly. And then he earned his PhD at MIT. After that, he spent a time at the University of Miami, where he got a tenure and became director of the Building Environmental System Lab until 2005. And then he became the Changjiang professor at the University of Tsinghua, where he is now also deputy director of the Institute of Built Environment. Along his career, has testified by an impressive score of publications, 120 conference papers, 36 patents, and a significant media coverage by journals like Nature and Wall Street Journal. He dealt with a lot of subjects like building energy systems, indoor pollutant sources and their control technologies, energy improvements of rural households, and building simulation. With reference to building simulation, he founded, and currently he is the editor-in-chief of the journal Building Simulation, and he also serves as associate editor of the journal Building and Environment Journal. He is currently a member of the executive committee and representative of China in the International Energy Agency, and he also has been advisor of many Chinese ministries and cities for energetic programs. So I think that I stole the stage for enough time. Today he is going to present his keynote about the role of simulation in preventing indoor air pollution, a foregone. So please, Dr. Yang, the stage is yours. Thank you.
Thank you for your very kind introduction. Good morning. It's really my pleasure to be here and to discuss something that I've been working on for the past 20+ years. As Francisco just mentioned, I'm the editor-in-chief of Building Simulation Journal. So I think I assume to talk about something about simulation. So that's a topic I'm going to share with you. And I'm going to focus on indoor air quality. Of course, simulation can cover a lot of things, but I think indoor air pollution, indoor air quality simulation is something that needs to be improved compared to energy simulation or ventilation simulation. So that's the focus of my talk today. So I'm going to cover IAQ, a little bit about the V, but nothing about EC. How do I move the PowerPoint? Is there this one? Yes. Okay. Okay. Yeah. So this is the outline of my presentation. So first is a very broad introduction about indoor air pollution. I think most of you are very familiar with this issue, so I'm not going to spend a lot of time on that. And then I will talk about the so-called simulation prevention approach. That's something I think is to me, I think this is important issue. And then I'd like to mention about simulation of indoor pollutant sources and sinks.
We still have the problem.
Okay.
It's not changed. Sorry.
Sorry. Let's see, because it doesn't show the play. This one, yeah. Okay. Sorry about that. Let's see. Okay. So outline, I just talk about the simulation of prevention approach, and also spend some time about the simulation of indoor pollutant sources and sinks. And then I like to use 3 examples. One is to show the validation of the model, and then the real applications, one in the building and the other one in the aircraft cabins, and then finally the summary of. So I think as a very general background, I think the requirement for the built environment and the buildings is very clear because people spend a lot of time, 80%, 90% of time indoors. So we really need safe, healthy, and comfortable indoor environment. And as you have heard from Professor Bruson's keynote speech yesterday, indoor air quality is really a very important part of indoor environment. To get a good indoor air quality, we really have to battle with many indoor sources. And for example, many of the indoor chemicals are emitted from indoor sources, like building materials, furniture. However, also some pollutants, like PM 2.5, could come from outside, especially, as Professor Chen mentioned, especially in some developing countries like in China, we sometimes have the haze problem. So the pollutant can come in to the buildings, and then we are facing both outdoor and indoor air pollution. So that's a big challenge. So generally speaking, we need to set up a standard, and the standard could come from health study or come from authorities like WHO. And generally, we need to make sure that the pollutant concentration level meets the standard requirement. And to get to that level, we have different ways of doing that. Source control certainly is the most important procedure. And also, we have sometimes have to combine with ventilation. And if these two don't work well, then you have to consider air cleaning. So the priority is source control should always come first. So what's the reality? What's the situation in real buildings? So here I just show you, it's a kind of a large data set collected by the China CDC. So they did a measurement in the new homes, and some of the homes are occupied, some are unoccupied. If it's occupied, then it's within 1 year. So they're all considered as new homes. And so they measure different chemicals, and actually the result found that, so the last column shows the standard of China standard, GB 1AA3, so that means you cannot exceed that level to be considered as acceptable. It's not superior, but it's acceptable. So from here you can see for many of the pollutants, formaldehyde, benzene, toluene, TVOC, so the average concentration already exceed the standard limit. So that means there is a huge percentage of the homes that don't have a good acceptable air quality. And the sample size is relatively large. It's in thousands of homes. And the long-term field study has also shown a clear trend between the time after decoration and the possibility of the VOC existing standard limit. So, for example, it's a 1 month home, then based on the study of more than 5,000 samples, 75% may have a problem either with one VOC or several VOCs. As time goes on, the trend is decaying. However, as you see, even after 2 years, there is still about 30% of the homes still have some problems with pollutants. So this really is a big issue. And although I just showed the data for China, and I think this is kind of common in many other countries, including developed countries. Actually, we have seen a lot of reports, although I don't have a very systematic collection of the data. So what could have been done to prevent this at the beginning? Of course, you can do the field measurement. Okay? That can identify the problem, but that cannot solve the problem. If you want to solve the problem, you really need to look at the early stage, design stage. When you put the material in, when you put the furniture in, you got to do something. Okay? You have to, at best, you need to show that after you bring this material in, they are not going to cause problem. So that's what we want to do. So foresee the potential problems. And that's not all. If you foresee the problem, then you can take action ahead of time rather than later time. If it already happened, then it's very difficult to do any remediation. All right, so that comes to what I call the so-called simulation prevention approach. Well, the idea is kind of simple. So before you do the real implementation in the early design stage, you do the simulation, and you try to find out what's going to happen afterwards. It could be long-term, it could be short-term. It depends on the time of concern. And of course, you can actually consider the different timing issue. For example, you have different materials, but they may not be brought into the building at the same time. You can consider that issue as well. So the key question is how to simulate the short-term and long-term air quality in the design stage, and how to validate the model. Because if the simulation is not accurate, then you cannot really provide any real useful advice. So here I just show the general risk analysis approach provided by US EPA. And of course, there are different levels of modeling, starting from the source modeling and then air quality model verified by experimental data. Either you do the chamber test or you can do the on-site test, because these are all physical measurements, chemical measurements. So you have the data. You can just directly compare back to back. And if you want to go a step further, go to the exposure modeling or risk estimates, then you can do that. However, validation is not easy because the risk is really not easy to validate. So with all this in mind, let's just go to some very general discussion about modeling and simulation. So first of all, you need to pick up a system. The system could be physical or notional. And also, we refer modeling as the physical or mathematical or logical representation of the system. So you simplify the system, and then you use an algorithm, do the simulation, and then predict the future. So this is basically what we are talking about. However, I have to say, modeling is not the purpose. The modeling is you are trying to develop some data. You want to predict something in the future so that you can do some preventive action. Why modeling? Well, I think many different answers you can come up. For example, we want to use models to understand a very complex world. We want to simplify the problem. And you can predict the future. And also, you can make better informed decisions. Okay? For example, when you design air conditioning system in this room, you need to model the air conditioning load and then select the size of the equipment. Otherwise, you don't know how big the equipment should be. Okay? So similar to the air quality. Of course, you can also manage the risk. And I would like to say that simulation is really not a single game. It's actually part of the scientific loop that involves many, many things, like experimental measurements, hypotheses, observations, and also simulation algorithms. So it's a part of the scientific process. Well, then maybe another question is why indoor air quality simulation not so easy? And I think for many of you who are familiar with building energy simulation or building thermal simulation, you probably have to agree with me that in that field it's well developed compared to the IAQ simulation. Of course, you can argue indoor air quality is more complicated. You are dealing with many, many things, not only temperature and energy. You are talking about a lot of pollutants, very complex mechanism and phenomenon. That's true. But I think the IAQ community could still learn something from the energy simulation community, because that's a very well-developed field. And a lot of people are working in that direction, not only in academia, but also in industry. Designers, they are very well-known. Energy Plus, so that kind of software. And also, I have to warn that although simulation could be very powerful, but there are many, many times that simulation cannot do many things that it cannot do. For example, it cannot substitute for the intelligent thinking. I think this is obvious, right? And it cannot do the things right if you don't do the right thing, okay? And it cannot totally substitute for experiment, although if it's right, doing it the right way, modeling can reduce the experimental time, but you cannot totally replace that without doing any measurement. So really, I think if you have that very good simulation tool, then you can really have something on hand and then achieve better goal. Okay? Although sometimes you are satisfied with the design already, but how to optimize that? If you have the tool, then you can get a better outcome. So here I just show the framework. This is actually just a very simplified version of the framework of IAQ simulation tool. First of all, you need to combine different kind of models, pollutant source model, ventilation model, the sink model, etc. And also you need to have a good number of data, meaning the database. For example, pollutant source database, ventilation database, and air cleaner database. And then you combine that, and then you do the simulation. You get the concentration curve, you get emission rate, and also you can get the contribution of each individual source or sink. So that's also very important, as I will talk about later on. So for example, if you want to decorate this room, this house, you have 10 materials. So usually what you do is you want to make sure each of these material is good. But how good they can be, that's a big question. So if I have a tool, then the first thing is I can measure each of these 10 materials, and then I get the emission pattern. And then I put these into the house. I can simulate what's going to happen. After you do one by one, then it can tell you, okay, after you get another material, it can tell you how much increase of the pollutant level it will bring in. And at the end, you can also find out the exact percentage of contribution from each of the 10 sources. And for example, material number 5 has a big contribution, and then you can go back and see whether you can do something with that. Okay? So this is the idea. So I think the main point is really you make everything digital, and you have all the numbers in mind, not just randomized trial. So, but as I just said, the simulation prevention is not easy. It's challenging because you have to deal with different pollutant sources and sinks. You have to look at complex mechanisms, and also sometimes you have to look at the influencing factor, like temperature influences. So I think everybody agree prevention is the best way, but in reality, people always go the other way around. So that's a very sad story. So next, I'd like to spend a couple minutes talk about how to simulate the indoor pollutant sources. We know, for example, the VOCs. You can measure VOC in this room. You can get a huge number of VOCs. Okay? So these come from different sources. Some of them are okay, but some could be harmful to our health. If it's higher than a certain level, manage to have a relatively good air quality. So the first step, what we want to do is you put the material or any potential source into a chamber. A chamber could be small, could be large, depending on the size of the sample you are talking about. And then you measure the dynamic emission curve. You get the data on the curve. And then you use a model to assimilate the data. And then the purpose of that is you get some of the key emission parameters, like what I've shown here. 3 key parameters: the diffusion coefficient, partition coefficient, and the initial emittable concentration. So as soon as you have these parameters, then you can extend the emission simulation beyond the experimental time. You can do the whole life cycle measurement, prediction. So this is the idea. So here I'd like to show you, this is the case I studied during my PhD study. I was more than 20 years ago. So I studied the emission from wood stain, which is a kind of a wet material. So I applied that material onto the oak substrate. Because it's a wet material, so it's very important to control the velocity about the surface. So I use an inner chamber to control the surface velocity. And of course, I also need to control the temperature. Okay? So I use a chamber to measure the emissions. And also I use GCMS to measure the concentration. That's routine. And also I use a very high resolution electronic balance to measure the emission rate directly. That means you get a weight loss, and then you know the emission rate. You don't need to do that by calculation. So after I have the data, then I have to consider to use a model. At the time, it's generally recognized that for wet material, people like to use this so-called vapor pressure and boundary layer model, like a VB model. So the key issue of this model is I assume is evaporation dominated, so you consider very important parameter, which is the convective mass transfer coefficient and also the emission mass left inside the material. So you can use that to try to simulate the data. However, after I did this, I found it only worked in the very early beginning. The first 2 hours, it's no problem. After 2 hours, no matter what I did, it doesn't match the data. So then I really thought maybe after a long time of trials and errors, and I saw that I may have missed some of the key emission mechanisms. So although the material is very thin, it's only 0.1 millimeter, okay? It's like a paper, but you still have to consider the internal diffusion inside the film and also diffusion from the film down to the substrate, all right? So after I do this kind of consideration, then I developed another model. Of course, the model looks more complicated than the previous one. However, this is more mechanistic. And for example, you look at the diffusion coefficient. Diffusion coefficient is not constant for the process. It actually changes during the drying process. When the concentration in the material changes, your D also changes. So this is also something difficult. All right. But after I do this and I compare that with the data, it has a very good match. And then I also did the full-scale chamber measurement and also verify that this model works okay. So that shows the emission process when you have to deal with the physical mass transfer. How about for some other materials like adhesives, silicon sealant, which is very popular used in buildings? These will involve some kind of chemical reaction. So during the curing process, you have the boundary, which is a curing interface. There is a chemical reaction occurs there, and then that generates pollutant. So that pollutant go out through another layer, which is a cured material layer. So you have 3 different layers here, and then just go ahead and develop the model for each of the layers, and then it can predict the emission pattern. So this one has the internal chemical reaction source, and also it can predict different phases at the beginning, first day, and then the second stage is for about 2 weeks, and then the last stage will be beyond. Okay, so this could be done also. And so that's about the sources. And using a similar idea, we can also look at the sinks. We know some of the material, like a carpet, they could be source for one VOC, and meanwhile, they could be sink for other VOCs. So use a similar idea, the mass transfer principle. You can consider both the surface absorption and the diffusion inside the material, so you can use this for the long-term prediction of the sink effect. Beyond all these materials, I think there's also one very important type of pollutant source we should not forget, and that is a human, ourselves. So like, for example, in this room, we have 100, 200 people, 300 people sitting here. So each one of us may not generate too much pollutant, but if you add them together, that will be a significant pollutant source. So I have to say the emission measurement from people is just in the early beginning. There has not much mature method being developed yet. So people are trying different ways to measure that. So what I'm showing here just one method. So use a sealed environmental chamber. Put the person there for short period of time, and then you measure the emission increase curve. And then use that curve, you can try to calculate the emission rate from the person. So this is still ongoing, but has shown some promising results already. So next, I'd like to use 3 examples to demonstrate what I have mentioned before. So the first one is about the long-term validation of the indoor air quality model. And so what I mean long-term, how long is considered? Wow. So we actually built a house, but the house is not occupied. Okay? We put one single material, which is a medium density fiberboard, which generates formaldehyde. So one pollutant source, one pollutant. So that makes things a little bit easier. So, and then we didn't control the temperature and humidity inside the house. So just let it vary with outdoor condition. So in summer, it's hot inside. In winter, it's cold inside. So just naturally change the temperature and humidity. And then we sample the air regularly, so 1 or 2 weeks per sample. And so the experiment started in 2012. So it's 7 years till now. So you can consider this kind of long term. Of course, you could not do this by real chamber test. And you can also not do this by the real on-site test because nobody, no family would allow you to do this kind of monitoring. So the result turned out to be quite interesting. So you have seen a very strong seasonal variation of the concentration. All right, so in the summer, it goes to a very high level, and in the winter, it just drops down to a very low level. And year by year, you see a decay. All right, so this is a very interesting phenomenon. And of course, we want to see what could cause this phenomenon. Okay, so the first thing we look at how does that agree with the temperature variation. So you see, really the concentration really vary very nicely with the temperature variation. So of course, you can, the first thing that you can come to our mind is temperature could make a huge impact to the emission process. And also we try to look at the humidity effect. And we try to look at relative humidity, which is on the right-hand side, not very well matching. But if you look at the absolute humidity on the left side, the matching is much better. All right? So that really means the absolute humidity could be a contributing factor to the emission from this fiberboard. And then, after knowing this, and we did some lab tests for the material, and then try to understand the mechanism. Of course, we hypothesized that the temperature and humidity could in fact affect the initial emittable concentration, diffusion coefficient, and partition coefficient. So when we had this mathematical expression, and then we use that, put that into the air quality simulation model, and then on the right side, you can find it has a good match between the simulation result and the experimental data. However, if you didn't consider the temperature effect or humidity effect, so you will see on the left side, there is a dark curve. That will be something you're going to predict. So we will go far away from the reality. Right? So again, this really tells us, if you want to use a model, you really have to have a certain level of credibility about the accuracy of the model. So the second example I want to show you is the IAQ prediction in a real building. So you see in China, many people live in this kind of high-rise, multi-family buildings. So we were invited to give advice to one of the apartments inside of the building and provide some comments whether what they need to do. So we actually tried to apply this approach. So we did all the measurements of the potential sources, and then we did a simulation, and we found that one of the artificial board may cause problem to the air quality. So we told the owner, okay, you better not to use that. Unfortunately, the owner didn't listen to us. Okay, they thought, well, so they still put it in, and then we did the measurement. So you see on the left, so after 72 hours of installing that board, we did a measurement. It was very high, 0.39 milligram per cubic meter. So clearly that's not acceptable. So we told them, again, we showed them, this is not going to be good, could be good. Well, the owner still hesitate because it's already installed. So hesitate. So say, well, let's wait a couple of days. So wait a month, okay? So wait a month and then did another measurement, the concentration is still there. Didn't decay. All right. So then the owner decided to remove that the pollutant source, the board. And then we did another measurement, and after a couple days, and then you see it was dropped sharply from 0.4 to 0.2, almost half. Okay. So clearly this shows, well, first of all, it's an unfortunate story. They didn't listen at the beginning. But through this process, we actually double verified our model. Okay, 2 times. The first time, after they put the material in, second time after they remove the material from the house. So this again adds some kind of credibility to the model. The last case I want to talk about is the air quality in the aircraft cabins. Well, I think all of us know the aircraft cabin is kind of a sealed, very much sealed environment. When it's flying in the air in 10,000 meters, outside is very cold, low pressure. You cannot open the window, of course. So they have to rely on the air that comes from the engine. All right, so compressed air from the engine and then cool it and then use that for ventilation. So that means the ventilation in the aircraft cabin is very expensive. Okay? But you have to rely on that to dilute all the pollutants that are generated inside of the cabin. So this is how it works. So part of the ventilation air is exhausted and part of air is recirculated. Right? So again, the key question is how can we control the indoor pollutant source the best we can so that we could minimize the requirement for ventilation, or we can improve the air quality inside the cabin. So to do that, the first thing we did was to do the onboard measurements. So we came to the real aircraft cabin, and we measure these parameters like CO2 particles, ozone, and also VOCs. I think the difference between the aircraft measurement and the building measurement is you cannot bring a huge equipment on board because they have very strict safety requirements. So all the equipment has to pass the security check. So that adds a lot of difficulty to the measurement. Anyway, after measuring more than 100 aircraft, we actually came up with this so-called target VOC list. It's still a long list, about 30 pollutants, but these are the pollutants that we probably need to really pay attention to. As you can see, although it's not a very large number, the concentration in the aircraft cabin is not high individually, but if you combine them together, add them together, so the air quality could still be not so good. So then we use the so-called forward method. Okay, so we try to figure out the pollution source inside of the cabin. So we categorize all these sources and sinks, and we try to understand one by one. So this is the first procedure. And then we get to the database. So collect the data and then try to see the potential contribution. And also we did another way, which is the so-called up-down method, or the inverse method. So after we get the measurement data inside the cabin, and then we use some model trying to figure out the contribute ratio from the pollutant source. So here I just give the final result. Clearly, human contribute a lot to this pollutant. So human include the breath and human skin. So that's one part of the contribution. Another one, also related to human, is chemical reaction between the ozone and the human skin. So that also contribute good amount. So, but other than these two, there are also some other pollutant sources, like the material, the carpet, and cleaning agents, and the air from the engine. So all these could add to the indoor the cabin concentration. So since the human is a very important source in this kind of environment, so we actually paid a lot of attention on that. We did real measurements of the human breath, collect the sample from the human breath, and then analyze that off the board, and then try to see how much generation of the pollutant from the breath. And also we measure the whole human emission, as I just mentioned before. And so also we use different chambers trying to look at the emissions from different source materials. So these chambers are from small to large, depending on the size. For example, if you measure the seat emissions, then you need to use a large chamber. And one very unique feature of the aircraft cabin is it operates under low pressure condition. It's not extremely low, but it's low pressure. So we also need to understand whether the low pressure can contribute to the emission rate. So actually, it turns out at a lower pressure condition, the emission gets faster. All right, so this is actually a very interesting thing from this study. If you didn't consider that, then you probably will mispredict the indoor concentration. And after that, you actually can do a lot of simulation exercises. So it's really in a very different scale, from macro scale in terms of meters to the very micro scale in terms of the human respiratory system. So it depends on the purpose. Okay? If you look at the pollutant transport inside the cabin, macro scale is enough. But if you look at the health effect, look at the micro scale. And this can also bring into the broader study, which is so-called human-environment interaction of air pollutants. Right? So human can generate different kind of pollutants to the environment. On the other hand, human can also uptake pollutant from the environment. So it's a so-called source and sink effect. Right? So if the human is a source, so that means you are polluting the air, which is not too bad. On the other hand, if you are a sink, that means you are taking pollutant from the environment. That can cause a damage to our health. So really, we have to distinguish these two things. But to do this kind of study is not easy because human is life. It's not like a material. So just try to summarize what I have just talked about. I think, as I said at the very early beginning, simulation tool can be powerful to prevent indoor air quality problem, but there should be conditions. Okay, it should be able to predict and assist in design, and also the model should be verifiable. Okay, and you should focus on problem solving rather than tool-led, and also the tool has to be used in good hands. And also, I think in this field there has been a kind of disengagement between academia, industry, and the people, at least in China, in my country, okay? Because we are facing severe problems, air quality problem, inside and outside. So there's a strong need from the industry, from the people. But the research kind of slow. The tool development is kind of slow, as always, right? So because research has to be rigorous. So how do we combine these together, okay? So research questions should come from engineering problems, and then should be able to guide engineering design or practice. And above all, it should be able to be higher than engineering only. So I think this is a philosophy I want to share. Right? So research, I really like this kind of words. Okay? Research has to be related to something that is practical and should be able to solve the problem. All right, so before I conclude, I'd like to just show you the journal, Building Simulation Journal. Many of you already know. It's a relatively new journal. It was established in 2008, 11 years ago. So it's growing very fast. So I'm very happy about that. So as you see, we have 5 fixed columns that cover different aspects of building performance simulation. So air quality simulation is actually in column C. Energy is on column A. B is about system components. And column D is about architecture and human behavior. And E is about advances in modeling and simulation tools. So I'd like to acknowledge Professor Yan Chen, who gave the keynote speech on the first day of the conference. He actually brought me into this field 23 years ago. So I did my PhD study under his supervision. And after that, I have been working on this field since all through. And so I also like to thank my former and current students who made a significant contribution to this work, and also the financial support from many agencies, or at least here only 2. Actually, we are funded by many other agencies. So that concludes my presentation, and thank you very much for your attention. Thanks.
Thank you very much for this interesting and stimulating presentation, particularly focusing on the importance of simulation and the way we use simulation, because this is a problem we have in several fields. Simulation tools are quite affordable, particularly in professional practice.
It can be free.
Yeah, actually. Yeah. You have time for questions. Are there any from the audience? Nothing? have one just to warm up the audience. With reference to the simulation and the importance of getting correct data, how the building process can influence, that is to say, you manage in the lab to collect data about a certain material, how the building process may influence that input data and how it is possible to cope with possible variations.
Yes, I think it's a very important point. The building process, actually, we are looking at different aspects. For example, VOCs, certainly the materials, you need to really pay special attention. So I think the first thing is really we need to get a large database. So for example, you have the larger the better. So then you know all the data. And also we have to look at the construction process. Other than the main material, bring in actually some of the side materials, what I said, the sealants. And these material could also contribute significantly. And also how they put that there. Okay, if it's exposed or it's underneath something, so that can make a difference. So, and I think also we need to look at the factors that are beyond this, for example, the air conditioning system. And also the people, how people occupy the building and how people use the building. So all these factors should be taken into account. But what I'm actually trying to say is certainly there are factors that can be easily controllable. So for example, the materials. And so these, I think you will do the best prediction you can. There are also some things that are not easy to be controllable. So then that causes the variation. All right. So anyway, I think this has to go step by step. So for the new building, I think the tool should be easy to implement. But how about the old building, like existing one, like this one? I think it's not easy to identify the source inside of this building. So then there should be another issue to talk about, which is the source identification. So that's another different thing, and I didn't cover that topic here.
Some question from the audience? Thank
you. Professor Yang, excellent presentation. We learn a lot from the presentation. I believe the most challenging issue that is with the simulation of chemical is their interaction between the contaminant and also the effect of the ozone in that environment, because ozone causes some chemical reaction, and that's the process. And that's information that's at this moment we should look about. What do you think about that?
Very good point. Actually, modelers began the physical process, so try to look at the mass transfer only. But later on, we realized that the chemical actually could make a huge difference, especially the ozone reaction and also the sealant, as I just mentioned, when you have the moisture transport inside the sealant, and then there is a chemical reaction over there. Yeah. So chemical reaction is actually more complicated. But actually, my understanding at the beginning was the chemical reaction has a very strict condition, especially didn't happen very frequently under normal temperature conditions. So that's a good news, other than ozone reaction, which is very easy to happen. But most other reactions probably is not too much we need to worry about. So I think we start from the physical and try to step by step, little by little, understand the chemical. And then maybe in the future, some biological issue should be taken into account, because that also can generate so-called BVOC, so that can cause odor or chemicals.
More questions? Okay. So I think that we can thank Professor Yang for his very interesting contribution once again. 1 moment.
Oh.